reflection groups and deformation.
Thank you, Alex. And I wish to thank the organizers of this lovely conference. Henry Wilton, Pierre-Emmanuel Capras, and David Fisher. But also, I wish to tell you that, also I wish to tell you that lecturing here has some special meaning for me because this is the first place, or this is the place where first I gave a public lecture back at 2000 in a very influential conference, and I was very young, and I'm very happy that this was not recorded at any in any fashion, and probably no one here remembers. Though I think, yeah, some of the older guys. I mean, if you've been there, you're getting old. I'm sorry. And also, I think I forgot to thank the organizers back then. So I want also to thank Katok, Margulis, and Polycott. And that conference over there was about rigidity. And this conference is about deformation, so it shows that we progress in time. And so I decided, I mean, it's about deformation, quantization, and approximations, of course. And but I will focus on deformation. And the main, the leading example in my talk will be the following reflection groups. Oh, recall the right angle pentagon tessellation of the hyperbolic plane. So here is the hyperbolic plane, or the disk model. And to construct this object, which is, I'm sure, familiar to everyone, you already make some deformation, or this, the most elementary way to see it is making deformation. Take an ideal pentagon and start move the vertices towards the center, and at some point, and it will get more and more Euclidean. I mean, to begin with, the angles at infinity are 0, and they get more and more Euclidean, and eventually you will get a right angle pentagon. And now, if we start reflecting it over those geodesics that we see here, I wish my picture was better, we get a tessellation of the plane, and we get actually also a group of isometries generated by these reflections, the reflections along these walls, S2, S1, S2, S3, S4, S5, and so on. The group is the group generated by this. It satisfies the following relation: Si square are all 1, and Si commutes with Si plus 1 in a cyclic order. So this is, I will not write the general definition, but I think everyone here knows that this is right-angled Coxeter group. Right angle because the powers of pairs of generators that give, I mean, every pair of generator either commute or generate a dihedral infinite group. Or maybe I put a star here and give some more lists also, it is so it's a right angle coarse groups by its presentation, as we see. Also by its construction, it is a lattice in the isometry group of H2, which of course we identified with P equal to R. In fact, the compact one. And in particular, it is Gromov hyperbolic. So this is a list of nice properties I want to consider. Moreover, gamma act on the boundary circle S1. This is not a generator, this is a circle. Gamma act on S1, preserving the Lebesgue. Well, it does not preserve what I'm writing now is incorrect. It does not preserve the Lebesgue measure on the circle, but it does preserve the Lebesgue measure class. So this means that whenever I'm this means that for gamma in gamma, nu, the Lebesgue measure, gamma nu is absolutely continuous with respect to nu. And then I can form we measure the difference by the Radon-Nikodym derivative of these two measures, which is a function on S1, actually an L1 function. Now, I want to give a general remark of the construction of a quasi-regular representation, unitary representation. In such a situation, now I'll use the same letter gamma, but think now of a general group for an action gamma on X nu. So X comes here to denote that this is a free setting, free of this example, where nu is where the class of mu is preserved. So people say sometimes nu is quasi-invariant, but this is not related to quasification that we care about here, of course. The map on the operation F goes to d gamma nu d nu at x square root times f gamma inverse x. So this is the map associated with gamma. Gives a unitary representation gamma to the unitary operators on L2 x nu. Of course, if the measure nu was invariant under the gamma action, then this term will disappear, and this is the familiar action. But in general, if the measure is not invariant, just taking the action by shift that we see in this component will not be unitary anymore. So we have to make this correction term, and we take the power of 1/2 to preserve this bilinear form given by integration of a function against another. Okay, I can write down the formula, but it's very easy to see that this is actually a unitary operator, and this map that you get here is a homomorphism. Again, if we take the action of gamma on itself, preserving the Haar measure or the counting measure, because gamma in my mind is countable, then you just get the regular representation, and this is termed the quasi-regular representation. In particular, I can apply this general construction in here. We may consider back to the notation I was using before without written notice, gamma into L2S1, Lebesgue. Now, so now the action on S1, or the action of gamma on S1, where gamma is a lattice in PSL2R, actually comes from the action of PSL2R itself, and I can apply all this to PSL2R itself, and maybe I should just write this. PSL2R acts or map to unitary representation on S1, which is G mod P with kind of a standard notation. And such things were studied probably from the early days of unitary representation theory. I'm not sure who to attribute the fact to that this is an irreducible unitary representation. Probably this is Gelfand or people around him. But the following theorem is by Cowling and Stiger. From 1991. As gamma is a lattice, so I'm not stating the theorem in the right generality. Their theorem is about lattices in Lie groups. And basically they say that such representation, L2 over G mod P, is still irreducible when I restrict it to the lattice. The representation is irreducible. Irreducible, of course, means that there is no invariant closed subspace in this Hilbert space. And my talk today is about various generalization of this. Again, maybe I will not write it down, but I will say it again. This is, of course, not the statement that you find in the Cowling-Stiger. They don't talk about this specific gamma. They talk about lattices in Lie groups in general. And such actions, the techniques of proving irreducibility is very much rely on the fact that there is a bigger group G, which is easier to study, and you use induction. This was taken further. Yes.
They good for any lattice? In a hierarchy group?
Yeah. Yes, but if you want to read about the actual state of the art about lattices, then this is what you should look at. This was generalized by Becker and Cowling in 2002. Study restriction so again, this is not the subject of my talk, but maybe I will say a word about it. If you take if you have gamma, a lattice in G, G is classical. I mean, G is semi-simple Lie group. This works also over other local fields, not only over the rings. And if you take a unitary representation of G, which is irreducible and not of a special type, it's not discrete series, then if you restrict this one to gamma, it stays irreducible. Okay? And this is proven using induction techniques, and I want to talk now today about more geometric techniques. I want to talk about situation where where gamma is not necessarily a lattice in a Lie group. So I want to come back to this idea or notion of quasi-regular representation, and to say that actually we know, given a group of favorite types, we know many such actions, so we may consider them. So I want to remind, or maybe I'll sorry, yeah, I mean, I stopped in the middle of this list just to recall something. So I'll come back here in a minute. So I'll use this board here. Fact. If gamma is hyperbolic, homomorphic group, for a given metric on gamma in the word Qi class of gamma, one constructs a measure on the Gromov boundary of gamma. So the Gromov boundary of gamma is a pure topological object. It depends, of course, on gamma, but it depends on the canonical, it depends on the metric of gamma, but only in some trivial way. It depends on the Qi class, which is canonical, of the word metric in gamma. But if you actually choose a specific metric, and now don't deform it up to Qi, keep it in mind, then you get a measure on this guy called, which I'm sure it is familiar to most of us, Patterson-Sullivan measure. And knowing dynamics of gamma on its boundary, this measure cannot be preserved, but this the measure class is preserved, which is quasi-invariant. Or again, the measure class is preserved. So our out of this, we can construct the boundary representation. Okay, so whenever we have a group gamma, hyperbolic group gamma, we can construct a variety actually of unitary representation. Why variety? Again, because we can change the metric. And the study of this in such a generality, or slightly more restricted generality actually, was began by myself and Roman Muchnik. And well, actually began much earlier than 2011, but this is the date that our paper was published. We studied boundary representation of group of the following form: pi 1 of compact negatively curved manifold. So for us, this is the first example, on the easiest to approach example of hyperbolic group, which is not necessarily a lattice in a Lie group, because the Riemannian metric on the manifold is assumed here. Is allowed here to vary. It's not a constant curvature, but it's not quite the class of hyperbolic groups yet, or the full class of hyperbolic groups. And okay, I'll come back to this. But oh no, maybe I'll put a picture here. So we have this manifold, and we have the universal cover of it, and we have pi 1 of m, this is m, acting on this, and also it acts on the on L2 of the boundary of the universal cover of m, again endowed with the so constructed Patterson-Sullivan measure. And we proved the analog of the Cowling-Steger theorem. We proved irreducibility. And also we discussed the dependence on the actual metric. I mean, you may think of this as, say, a surface of genus 2, as in the picture. So the fundamental group of the surface is the same, whatever hyperbolic metrics say you put on the surface. So you get the same group, but given different hyperbolic structures on the surface, you get different measures on the boundary a priori, and I mean, and you get the Teich-Miller many variety of such. And what we also showed is that we show that the dependence on this metric. If you take different metrics, you get different unitary representations. And all are irreducible, yes. And in fact, all are, I mean, there is a full invariant. Given a metric on the group gamma, one can, out of the metric, come up with the invariant called the Mark length spectrum. And this is some sort of a character that it's conjugacy class invariant on the group gamma, and this one is exactly the full classifying invariant of those boundary representations. Okay, but I don't want to talk about this in this generality. I want to keep talking about generalization. There is a quite recent, beautiful, or maybe before writing this, and with Roman Muchnik, we had in mind approaching the general setting of hyperbolic groups. We had a program, but somehow we never get to this. I will say a word about our techniques later, and it was kind of complicated. I think it is achievable, but quite recently, Łukasz Grancarek, a student of Jan Dimara, former student, in his PhD thesis, generalized this in a beautiful way. So I suppose this paper will be published in 2017 or 2018. Boundary representations of hyperbolic groups are irreducible, and also maybe I didn't meant to mention this, but I already did. So I'll add this remark, and classified by the metric. Up to similarity. This last bit also depends on the fact that somehow, and again, I hope this will be clear down my talk, that sometimes you look at the action not only on the boundary, but the boundary times boundary, and use an ergodicity result of the particle solver measure of the boundary times boundary that we proved with Alex Fuhrman. Okay, so that was my first page. Where's the result? And of course, I promised to come back to this group gamma and to discuss deformations. But before, I want to ask the general question of take the general question of you have a unitary representation of gamma on some Hilbert space, and you want to prove irreducibility. What are the available techniques for such a thing? How do you approach this? One way, as I said before, would be, if gamma happens to be a lattice in a Lie group, to induce and discuss the induced representation. That would be very nice, but many times you don't have these techniques, and you want to come up with a more geometric technique. And so how do you go? So what I'm telling now is far from being geometric. It's, but here's the first step to do. This representation is irreducible if and only if you look at the commutant, the centralizer of gamma inside B of H, and this is just the constant function. B of H here stands for the bounded operators. On the Hilbert space, of course, if my representation decomposes into a direct sum, I can find the projection onto one of these pieces, the orthogonal projection, and this will be an element in here which is not a scalar, but also operator theory tells me that the centralizer of something is a von Neumann subalgebra. It's closed for the weak operator topology, and there are many projections in it. Okay, so so this is how the if and only if goes. I can pair this or double this with the double centralizer theorem. The double centralizer theorem tells me that it tells me the following: that if you take gamma, I think of gamma inside this space, and I take the span and the closure with respect to the weak operator topology. This is the double centralizer of gamma. And if the centralizer of gamma is just a scalar matrices, everything that commute with matrices is everything. So this is all B of H. So let me get this. The representation ρ is irreducible if and only if this happens, and this happens if and only if that equation happens, and this side here equals that by that theorem. Okay, so so here is a strategy of how to prove things. Try to look at everything that's generated by gamma and prove that it is everything. So so the method that we had with Roman-Muchnik is the following. Express every rank 1 operator in VH as a limit, as a weak operator topology limit of linear combinations of elements of gamma. So I think I will come back to this in a minute and explain how this goes, and explain also what Gansarek did, which is smarter than what we did. But before, I have to tell you about the following trick, which we found with these two brilliant guys that I was lucky to work with, Adrian Boyer and Ukash. And and now I'm telling you another trick of how to prove irreducibility. Maybe you've seen it. I haven't seen it before, but it's one of these tricks that makes math so beautiful, but also so frustrating. I'm about to tell you a criterion for if and only if for irreducibility. Maybe you haven't seen it before. I suppose so. But once you see it, it seems that it was always there. And you don't feel like you discovered something. You feel like you knew it all the time. So even if you didn't care about what I said earlier, I think this is nice. So look at this. I'm claiming that, again, this guy is irreducible if and only if, now I'm looking at rho gamma, tensor rho gamma, inside bounded operator on the Hilbertian tensor product of H with itself. So I'm doubling H, and I'm taking the closure here. And I'm asking myself whether the flip is an element in this space. So on H tensor H, this is direct sum. I mean, this is just sum of little pairs of tensors with appropriate completion. I can flip the coordinates. So this is the flip operator. I will not write down a formula for this. I hope this is clear. And maybe it sits here, and maybe it is not. It does not. And this is equivalent to irreducibility. And here,
What is the flip?
on H tensor H, on a vector space tensor with itself,
Yeah.
I can just switch the order of coordinates. Right? This is a bounded operator. It's norm 1 operator. It's an isometry. Very naive one. But actually, it is related somehow when I think of boundary times boundary. And I will not elaborate on this, but I have to say it. I think of the boundary of a Gromov hyperbolic space as the space of future random walks. But also I can think of it as the space of past random walks by changing, by looking backwards. And the boundary times boundary is the space of by infinite random walks. And flipping is just changing the orientation of time. So this is really influential observation in my mind, but here this is completely algebraic, of course. You don't have to think of it this way, but where did I put this? So, yeah, let me explain this. If rho is irreducible, then rho tensor rho is irreducible too. And then this guy here is everything. Oh, maybe this guy here is an equation. So obviously the flip is there, right? On the other end, rho not irreducible, then H is H1 direct sum H2 in an equivariant manner, and then consider H1 tensor H2 as a subspace of H tensor H. Of course, this is, since each of them is gamma invariant, this is gamma times gamma invariant, and if the flip could be approached using combinations of elements in gamma times gamma, then I can switch it, but this is not flip invariant. Contradiction. Okay?
Why is rho tensor rho irreducible?
Sorry?
Rho
Oh, this is a general fact about unitary representation. That it's irreducible as a representation of gamma times gamma.
Gamma times
Yeah. Yeah, this is important. I moved from representations of gamma to representation of gamma times gamma. But so this trick enables me to judge whether a representation is irreducible, maybe by moving to another representation of the product of the double of the group. But you have to actually exhibit only one operator over there. If you want to approximate, to make an approximation, this is really remarkable. Actually, obviously, I didn't plan my time well, and I'm not getting near deformation, but I do want to tell things in this order. I want to make a certain conjecture. that I'm working on with these guys, that for boundary representation, we have an explicit sequence. I'm denoting by gamma n the elements in the ball of radius n in gamma. Okay, I will not write down this on the board. I hope this is clear. So you average on balls, and we take the elements. This is an element in gamma times gamma. The anti-diagonal embedding of gamma in gamma times gamma is not a group homomorphism, of course. So this cannot be seen as an element of a smaller group, gamma tensor gamma minus 1. And you have to normalize it in a certain manner. This function over here is called the Harishchandra function sometimes. And so this meant to mean something to you if you've seen such things before. And this should go, when it goes to infinity, in the weak operator topology, to the flip as an element of B boundary gamma times boundary gamma. And again, the fact that this should converge to that thing is really related to this thing I only hinted to you about saying that what is happening here is really that we change the orientation of time using such averages. Yes, please.
I mean, this gamma 1, 1, right?
Gamma 1, 1?
Yeah, that's a function that decays at infinity. So you want to divide by something.
Sorry?
You want to divide by gamma 1, 1?
Yes.
Because it gets, that makes the sum blow up somehow.
But also, I mean, here when you act, there is a, you use, somehow it concept.
I can't, yeah, okay.
Okay. You have the factor which is the square root of the Radon-Nikodym derivative, and somehow this is a normalization term that should take that away, in a sense.
Oh, it's not unitary, you say?
Rho is unitary. But of course, making convex combinations, it's not unitary anymore.
It's not convex.
It's not convex. No. If it would be convex combination, the norm will decay. So it's normalized, so it is not convex. And so this is delicate. Maybe I should say something again. I didn't plan to, but the fact that these converge to that is correct, is known to us. This is the find of Adrian Boyer, but we don't know that it happens in the right norm. And there is a very delicate issue over here that we don't know how to justify yet. But I truly think that this is correct, and I like it a lot, even though I didn't give the right introduction to make you impressed with me with this. I think it's a new phenomenon and a nice one.
What gamma n is?
Sorry?
Just say again what gamma n is.
Gamma n? Gamma and gamma normal thing. The ball of radius n.
Right.
Sorry.
If this is true for random walk instead of if you don't average over a ball but average over a random walk?
Yeah, it should be the same, I think, but there are a lot of technicality here, so which I don't know how to deal with. So then I should say probably yes. Maybe I'll say a word about our strategy with Roman Muchnik. I told you that what we want is approximate every rank 1 operator. So start with approximate the operator to take f to What is a rank 1 operator, by the way? Always take a vector, apply a functional, get a scalar, and multiply this by another vector. Okay? So take given f. The two vectors that I want to use are the vector 1. 1 is the constant function in L2 gamma, in L2 boundary. And we showed, so that a similar kind of call this T. We show that now this is happening, unlike this thing I conjecture that is happening on L2 of the boundary times boundary, this happens in L2 of the boundary, and we show that we have the right asymptotic over here. And maybe I say some few more words about this technique. More generally, consider f goes to f paired with chi u times chi v. Here, u and v are open set of the boundary. So we've seen that 1 over gamma n over certain set of this expression tends to I don't know, call it S. SUV. And I want to say a word about it, of how one goes and proves such a thing. So recall that with Roman Muchnik we discussed fundamental groups of surfaces or negatively curved manifolds, and recall that the boundary fixing a base point. The boundary could be identified with the unit tangent circle over that base point over here, and one can relate this problem to a geodesic counting problem. We can look at we can think of u and v as subsets of the unit tangent circle and consider geodesics. I will not write down formulas, but that go out of here, through out of our base point through u, travel around the surface, and coming back and close up through v. And one can study the asymptotics of the number of such geodesics, and this was done by in Margulis' thesis, and he showed that asymptotics of number of geodesic of a certain kind tends to the measure of u times the measure of v, which is so you count the number of geodesics with this property of a certain length, you normalize properly, and you look where it converges, and you get this equidistribution formula, and this is some manipulation of that formula that we managed to do, and this actually using this method here, which I described, give us the full proof. Garanzarek has a smarter method. Without relying on a specific asymptotic. Okay, which I guess I should not I really badly plan this talk because I'm getting to the main subject only now. Sorry, guys. But those things I wanted to say anyway. Back to our right-angled coxeter, or hyperbolic coxeter group. We're back to the group of reflections of this object here and generalization of it. And let's call it now W, as it's common. And let's talk about deformations, the Yohoi. Okay, I'm not sure. Algebra. So take the group algebra, CW. Here is something that works for every coxeter group. Take a parameter, Q, and define new multiplication. So again, this is a vector space. W is not a finite coxeter group, it's an infinite coxeter group. But in any case, I have like the standard convolution operation, and I need to explain what, when obviously ES and EW denote the generators of this algebra, I need to explain how to take the product of such two. And this should be ESW if I made no deformation, and I keep it if we have this inequality. Otherwise, instead of taking ESW, I mean, I will take ESW, but only with coefficient Q, and the rest I will keep EW. And this is otherwise. So this is a deformation, and I hope in a few minutes to explain where it actually comes from group theoretic point of view. And you get an algebra called HQ. H1 is just the usual group algebra. And so this is a piece of classic theory. And now I want to tell you how to deform the boundary representation. So W, the reflections group act on the boundary, and again we have the boundary representation in L2 of S1. It's a unitary action. So the group algebra act by bounded operators, And now I come up with the formation of the group algebra, and I claim that it deforms within B of L2 S1. So I can deform the group algebra accordingly to this Q parameter within, so the Q here should be a complex number a priori. If you take F in L2 of S1, again, one can generalize this, but I want to stick to simplest notation as possible. I can define.
Why did you say that H2 is W?
H1.
H1. Oh, sorry, yeah.
Sorry?
No, it's okay.
I'll define rho Q S of F at X. So I'm defining a new operator, rho sub Q, which will be Q to the 1/2 or 1 S of F if X is okay. Now this is S. This will be a S minus and S plus. The reflection on S divides the boundary, the space, and the boundary into two pieces, which I will call S minus and S plus. So if X is in S minus, I will apply this formula. Otherwise, I will apply that formula. Of course, the formula is not that important. What I'm trying to say that there is a deformation of H representation of HQ in B of L plus 1. And truly my time is up almost, so I'll give you the theorem. We know that for Q equals 1, this is irreducible. What I claim is that for Q bigger than 1, these are all irreducible. Now I'm looking at this clock, and but in the very last minutes, I want to tell you how this is related. Just write this as a slogan. Related to representation of group acting on hyperbolic buildings. Koji asked me before my talk if I will ever get there, so apparently I didn't really. But okay, out of this thing, out of these reflection groups, one can construct a building. Just by whenever you split the space into two, I can add many copies of this and like many pages and go on as we do in building theory, very roughly. And assume you have a group G act on such a beast, and it acts sufficiently transitive. It acts transitively on chambers, apartments. This is what we call strongly transitive. Then I claim that this will be a hyperbolic group, not countable, but locally compact hyperbolic group. And I could consider the boundary representation associated with this hyperbolic group. And there is a standard technique to study a unitary representation of such things by you take G, you take a maximal compact in it, and you take a representation of G, and you look at the space of invariance for this maximal compact, and this is acted upon by not the group algebra, but a smaller algebra, which is nice to study, the algebra of bi-k invariance functions on G. So this is something very standard. And the thing is, and this is somehow how deformation theory works for Coxeter groups, it is known that, we show it specifically in this situation, that when you start up with such a thing, hyperbolic building, and you look at the algebra of bi-k invariance, when k is a stabilizer of a chamber, you get exactly such deformations of the group algebra CW, where Q here is an integer number. This is the thickness -1. So this irreducibility result over here prove irreducibility result of some more monstrous beast, which is harder to approach otherwise. But somehow it also shows that the irreducibility results of hyperbolic building is only, it can quantify it in a certain sense. It's just an instance of a more general irreducibility results of a family of deformation of the group algebra of the Coxeter group, which its own irreducibility is a classical result. So this is what I wanted to tell you today. So thank you for listening.
May I ask two short questions? One, just for my ignorance, I mean, like, you are really working here with, not with general representation, but representation which are coming from permutational representation. Like for finite groups, there are some conditions, like if it's a two transitive, then you get automatically reducibility of the associated unitary representation. Are there criterions like that if it's like two mixing or something like that, then maybe one can use it?
This is an excellent question, because one feels that they're supposed to be. With Alex Fuhrman, we proved a general result about the action of a group on its boundary with a Patterson-Solvent measure, that this is doubly ergodic. So you have double ergodicity on the boundary. It's morally it's the same as two transitive, right? But since and certainly this is important. This is an important ingredient in proofs, but by itself is not enough. Or at least we don't know how to promote this into full proof, because
examples of groups acting doubly ergodicity.
Yes.
Still not
Yes. Yes. And maybe I should tell you exactly where the difficulty comes. In finite group theory, the measure on the boundary or whatever space of permutation you look at is invariant. In boundary theory, typically the measure is not invariant. So there is an open question in this field or in this circle of problems, is what happens if instead of looking at hyperbolic groups and its Gromov boundary with Patterson-Solvent measure, what happens if you take arbitrary group and you consider a Poisson boundary of it, Fürstenberg-Poisson boundary? Then you can still ask, and I think this is a very interesting question, whether this is irreducible. In that case, at least if the measure, the random walk measure that generate this Fürstenberg-Poisson boundary is symmetric, then we know that the space is doubly ergodic, but we don't know how to prove the irreducibility in general.
Second question. As you know, now there are a lot of things which are true for lattices. We try to kind of extend to thin subgroups.
To?
Thin.
I think.
Is there a chance that something like that will work for subgroups which are not lattices, but still dense enough in some sense?
There is some chance. I mean, the thing is that if you take a thin subgroup, maybe the measure that you consider on the boundary I mean, typically it will not be fully supported, or it will be something much thinner than the Lebesgue measure. You have to change the measure on the boundary that you look at.
No, but don't take the boundary of the group. Take like subgroup of infinity in the
and
piece and acts on the boundary of the Lie group. Let's start with this.
Okay.
I mean, typically, if you take a, let's say, geometrically finite subgroup in a hyperbolic n space, then the feeling is that the complementary series which are near the identity are going to restrict irreducibly, because these tricks you're doing over there, they're typically of the sort, you know, once you restrict coefficients of your representation, they become integrable or L2 on the group, you're dead. You can't be irreducible. So that just means that there is this region in the complementary series which you can quantify in terms of the critical exponent, which I think you're going to get irreducibility by using these techniques.
I suppose in some cases, but I want to say that if you look at examples of convex or compact, I mean, there are groups that their action on the boundary with respect to the Lebesgue measure will not be ergodic anymore. And then there is no chance of getting irreducibility for L2 of the boundary with the Lebesgue measure.
So this will be the replacement of the pin instead of Zariski bands, and take this as a definition that it's that the action is still ergodic.
Okay, so maybe, and maybe I need to think about what Mark said. I cannot do it here, but maybe there are some replacements.
Here you're really looking at the center of the principal series, which
Yes,
triggers
yes.
gamma, right?
Yes.
And once gamma is too small, then that you're going to get L2 very easily.
L2 of gamma.
Exactly. So
Yes.
you get reduced.
Yeah, right.
You want
Exactly, because you're acting in a dissipative fashion.
You may want to play the same game, but with a representation which is more towards the identity along the principal series. So this makes sense in a rank 1 situation.
But maybe in another direction, one sort of answer I want to make is that in a minute, you can change the measure that you look at the boundary to a measure that fits naturally the thin group. And then there are some recent works of Adrian Boyer in this direction, very interesting ones.
Okay, let's thank the speaker again. And borrowing a couple of minutes from the coffee break.